All right, we're going to continue with our discussion of results reporting in neuroimaging. And now we're going to start looking at some examples of how to present results. And for that, we're going to use a specific set of data. So this comes from a fairly widely known data set now from the NARPS project from 2020. And what this data is task fMRI data with a mixed gambling paradigm. And the two groups involved were each about 54 subjects that had 4 EPI runs apiece and fairly high resolution fMRI data, 2mm isotropic. And this data was used and made public, and researchers were basically asked to self-organize and analyze this single set of data however they saw most appropriate using their normal pipelines, and then present their statistical results about a few specific hypotheses or questions. And in the end, there were about 70 teams that participated and submitted their results. And then the first authors here studied these results and discussed some of the variability that was seen in them. And we're going to spend some time looking at this data and both in terms of this larger group analysis, but also just for some other lessons for results reporting. So in the group analysis that we're going to discuss here, we used AFNI and particularly AFNI proc with a fairly standard pipeline. We used nonlinear alignment to the MNI template, 4mm blur. Remember, the voxel size was 2mm for the EPI. We included pretty standard motion censoring, and for this task data where there was the mixed gambling task, so there were losses, potential losses and gains that were provided to subjects that had different magnitudes. We used the response time for amplitude modulation in the regression modeling. The scripts and the paper describing this are both public in this GitHub repository, and there are actually a fair number of parts to this paper, including single group results, or kind of just how an individual group would report results, both for voxel-wise and ROI-based studies, and then also about meta-analyses. And we'll talk about a couple of these here, but mostly focused on the voxel-wise analysis, but you can read more about the other parts. For the cross-study comparison part, so the original NARPS project, as I mentioned before, had 70 teams analyze the data and then answer some specific yes-no questions about hypotheses, and those were tabulated and compared for variability. The teams were also asked to upload only their unthresholded statistical maps. And going back to the first part of this lecture, it's a shame that the effect estimates weren't also emphasized. But in this case, it is nice that the statistics maps were then made public on NeuroVault with one link per team, and those are available. And we're going to look at these here as well to get a sense of the actual variability of the data in more detail. Okay, so that's the data we're going to use, and let's look at an example of better thresholding for representing results from a single group study, let's say. So this is what it would typically look like if you did an analysis and this was a task fMRI study and you answered your question and you have your contrast of interest. And what will happen mostly is people will threshold their data at the sacred value of P of 0.001 and then perform a cluster-wise or second-level correction for multiple comparison adjustment at 5%. And then this is a pretty standard way that a figure might be shown. So the idea would be that wherever you see color now are these significant results, and there you go. And you don't need to know anything else about any other part of the brain. So the researchers have decided this is all you need to know, except for the fact that here, or even here, we don't need any information. Okay, and this is, I think, what we've been used to seeing for brain imaging published in newspapers, papers, conferences, etc. But it does raise the question of, well, why is this here and very lateralized, and what happened over here on the other side? And anyways, what do we know about it? We know nothing here. So what about looking at the results this way? So this is using transparent thresholding that was recommended by Allen et al. In 2012. as a way to show more data. And what we've done is we've allowed things that are below threshold to still be shown, and how they're shown in a way that emphasizes their statistical reliability still is that things that are just below threshold are nearly opaque, and then they fade down to transparent as the significance drops. Okay, so where we see things that were still above threshold are outlined in black and they're opaque, and things that were near threshold but not quite, just below, those we can still see pretty clearly, and then where it appears clear, that's just because the reliability or the statistic value is so small that now it's transparent. Okay, so let me just go back and forth between these two views. The original view and the new view. Original and new view. And the thing to notice here is just how much more information is here. And there are interesting things like this region that has high yellow, hot color values here, high positive significance. Actually, you do see something that is kind of partnered with it on the left side of the brain here, but at lower significance. Or you see this region here actually represents something across this whole sulcal gyral pattern here, and there is something kind of left-right homologous here. Or this region has a left-right partner here that you wouldn't have seen at all. And maybe if you added more subjects, these would become more significant, or maybe some of them would go away. But something like this and like this look like they might be of interest. Now, if you're going to compare your results with your study of 54 subjects here to someone else that maybe has 100 or 200, and they might see these regions as significant, if you just look at your results this way, you would see differences. But here, you actually allow for more information to be shown. And it's true, the immediate objection that some people have is just, well, it's below significant threshold, therefore it must be wrong or bad or incorrect or not active. And I think part of the main purpose of this talk is to convince you that that's probably not a good way to think about neuroimaging for many reasons. And this arbitrary threshold of p of 0.001 could easily be of p of 0.002 or p of 0.00005. Why should this value be the exact arbiter of everything that is on and nothing else we need to know about? Anyways, once you see this information here, it's pretty hard to go back here and think that this is informative or maybe enough information. Or at least this is what I feel about it. And what we're really discussing here is what is adequate to say what your results are of your study. Here you have very little information. You're reporting on something like 2% of the voxels of your brain. But we actually analyzed everything. Simply, why not show the results that are everywhere? And even if they are below threshold, there are still results here that are worth thinking about or knowing about or reporting. And in this way, I think it's nice that you still balance highlighting the most the most significant regions, the more fundamental ones that you'd want to report. That is still clearly messaged here. It's just that you see the full context of everything more informatively. Okay? And actually, myself, I would prefer to see the results this way. I have no problem with seeing statistical results outside the brain. The data were gathered in a full field of view. And actually, I kind of want to know whether it's just a little bit of random noise outside the brain, or maybe there is some structure here. It would maybe help me see ghosting or alignment artifacts. And these are all really important things. And we'll look at the data even that was in the NARP study and see why this matters carefully. So there's a bit of a culture change, I think, to be comfortable seeing this with what we're used to seeing this and being okay with seeing results that are below significance, but they still have information. And frankly, I think that this would be the best way to go. Okay, now it's important to note that there have been previous studies that talk about trying to show more results in neuroimaging. So obviously the Allen et al. Study here put forward this idea of transparent thresholding, and I think this is quite useful. There were other earlier studies that looked at presenting color bands of just the statistical results, or not thresholding at all has been an idea put forward, or model summaries that include several pieces of information. Okay, so these are all important, and they get at this idea of showing more information is better. Personally, anyways, it has to kind of balance the amount of things that you show and the pieces of it. And that we're going to focus on the one described here from Allen et al. And show why that one might be useful there. But there are other ideas that are worth considering too. Okay, the important thing here is that how you visualize your results is how you understand your results, and also how readers understand your results as well. And with what we call all or nothing or opaque thresholding, all you see are these things, and you fall into this language of these are the significant regions, these are the active regions. And frankly, that's just simply not the case. You're heavily dependent on your threshold, which is arbitrary, even if you like a round power of 10 p-value. It just is arbitrary. You waste a lot of information because there are results here. There is model fits that you've done everywhere. You acquired data everywhere. Why waste the information of what you found there? Because as you add more subjects or something, some of those may become significant, and it becomes much less of a change. You can actually show some of that information now. Hindering interpretation, frankly, this is not the only thing that's happening in the brain. Also, noise is not constant across the brain. So even if you apply a single p-value threshold across your whole brain, the fact is your local signal-to-noise ratio is different, so you're effectively using different criteria to threshold even within one dataset, let alone across studies. You won't know about poor modeling because you can easily just see blobs that appear here, but you won't see things that might tell you about unrealistically large or small fits in other parts to realize that this is a problem. And it harms reproducibility. Your study is only showing these blobs here. Another study of more subjects or of a slightly different gambling task might have regions that are slightly different shape, and then they're going to look fairly different fairly quickly. Consider thresholding here. Well, this is more consistent with biology. We know that the brain is not simply on-off in a given region. If you ask me to do a task, my brain is not suddenly on-off localized, and particularly the bold response is not on-off. It takes a while to go up and come down, and it has a 15-second on-off time. And within a given sulcus and gyrus, there may be some parts that are more active and less active. There's a little bit difference than on-off. Also, when you report results scientifically, you want to say what your results were everywhere. And even if you want to say still that these are below significance, that message is still highlighted. You can see quality control issues. For the comparison now, when two studies have different results, or if they want to compare them, they have a much richer set of data to compare. If you're comparing these and you say your blobs are different, if you don't see the full context, you might miss out on why they're different, or the fact that maybe in a different study, this is just below significance, and you would see it if you had allowed it to be here, and it would be nearly opaque, and you would understand that. We should be worried about arbitrariness. This has decided, and the key word here is decided, that these are the only things a reader needs to know about. Now, that decision comes at a particular threshold. People may think that P of 0.001 is a reasonable threshold, but there's no reason why that is inherent to biology or to the scientific effort or anything like that. It still is arbitrary. Using transparent thresholding reduces the influence of that arbitrariness. Here, if you add a couple more subjects or if you change your p-value a bit, your cluster picture would change drastically. Here, it won't actually change that drastically because you will have some things that are a little bit above and below threshold, but you'll still see them all with almost the same amount of influence. So this method here is providing evidence for what's happening in the brain. This is providing decisions. And I don't see any reason why a single paper should have to provide a decision. If a single paper says these are the regions involved, that's it, I've decided it, no one else needs to study it, that's unrealistic. When we're presenting our results from a study, we are providing them for conversation. We're saying these are my results, let's see if other people find it with their data or reanalyzing it and for comparing them. And if I decide based on some p-value that these are the only things that matter and someone else decides that they have the only clusters there, it's very easy for small differences to actually, in processing or in the subject acquisition or the paradigm, to make these clusters differ in shape a little bit, and your meta-analysis really could be thrown off by that. You're very, very sensitive to small choices in your decision-making for how you do your analysis. Here, you can do a much richer, deeper analysis. You're not just comparing a few things, you're comparing everywhere in the brain, and you can really highlight where there's more agreement and differences. This provides a much richer picture of what's happening and provides a more realistic picture for meta-analysis. This one is highly sensitive to all the different decisions you've had to make about your blur radius, your sensor threshold, all sorts of things like that. How many subjects you have, how many trials you have. This is much less sensitive to that. So for all these reasons, this seems more biological, mathematically sound, and scientific. Okay, now let's talk about another issue for reporting results related to peak voxels. So it is quite common for people to summarize their results that we just looked at, like those clusters, let's say, from the first image. It's common to use the peak statistic location to define what that cluster is. So you might make a table and say, for each cluster, these are the coordinates of the peak value, and these are the ROIs that they fall into. And I think here we're using the Glasser Human Connectome Project Atlas in M&I space, and that's what each of these are. So you might say, fine, that is it. And so now in my study, these are the regions. Let's see if you get the same regions in your study. But there is a problem here. The peak statistic voxel location isn't the only relevant part of the results. There was a whole cluster there. And remember, statistically with clustering, once you cluster, actually, you don't really care what the values of the statistics are inside. That's what it means to threshold your data with like a null hypothesis significance testing. So picking just one arbitrary value like the peak location is not really summarizing your whole cluster. And it's actually known that statistically, peak statistics are really quite unstable. If you add another subject, if you change something in your processing, that peak might move around. And another way to look at the instability is, well, what if I wanted to use not the peak statistic location, but the central location of the voxel, of the region of interest? Well, if I did that for these clusters, this would be the table that I would get. So this is the coordinate of the center of mass of that cluster, which is another reasonable way to try to summarize it or say where it is. Now, if I flip back and forth between these for a second, what do you notice? This is if you summarize your region of interest with the peak statistic, and this is if you use center of mass. Either of these could be reasonable values, but what do you notice? It's not just the coordinates changing, but actually now your reported region of interest in your atlas has changed. And this is what it looks like, that just by choosing a different summary single location for your region of interest, you actually have a different coordinate, a different location that you're talking about. In one case, this even flips from being a right-sided region to a left-sided region. The clusters that we get out of our voxel-wise analysis and things like that, they're pretty messy. They don't necessarily just fall within one region of interest. They're not always blobby. They have some linear structures. Consider here, if I go back to this image, this is actually all one cluster here. You don't see it through this slice, but they're connected in different slices. What does it mean to try to summarize this long linear shape that moves across different parts of the cortices by a single voxel? You might make the case that a blobby region here might be easy to summarize with a single location, but most of the regions that we get, the clusters, are not easily summarized by a single voxel. And this commonly used method of peak voxel summary and then entering this into meta-analysis just really sets yourself up for non-reproducibility, because whatever you use as your single summary voxel location is highly unstable. And the peak statistic alone, again, as I mentioned, is known to be mathematically unstable. Adding another subject, changing your blur radius could easily change this in the same way that you would be falling into a different area of the brain even. So summarizing your cluster results using just peak voxels seems setting yourself up for reproducibility problems. You can't even reproduce a lot of your regions if you choose a different central measure for your cluster. So is there a better way to do this? And I'd like to make the case that yes, there is. What you could do is you could look at your cluster of interest and say all the regions, list the regions that it overlaps with. This provides you a better summary of the information of your cluster because, again, most clusters don't fall within a single region. Now notice here, the size of this cluster is 551 voxels, and it actually lands in 3 major regions in this atlas, and we wouldn't have known most of this information by just the single peak voxel summary. In some cases, sure, the voxel primarily falls in a single region. That's great. But in most of these cases, it's actually in several regions. So this is much more informative, and this is much less sensitive to an arbitrary choice, like whether to use the peak statistic or the center of mass statistic. So this provides a more stable basis for reporting, understanding, and for meta-analysis. And remember, the results of any individual study are not going to be taken on their own. They're going to have to be contributed to the literature to compare with others, and this is a more meaningful way to present your data for a more accurate comparison, a more informed one. And it even allows for the idea that you could talk about clusters that have a lower p-value. So getting back to the idea of thinking about not being so sensitive to arbitrary thresholds, because where you draw your clusters is sensitive to that choice, you can actually still accommodate in this model regions that are maybe of interest, and the researcher is welcome to decide what those are that they want to talk about. So I would maybe come down to the idea of choosing your significant p-value and definitely reporting all the clusters here in this way. But then, we are researchers, we have other interesting information and background information that we know about. It might be possible to also choose clusters to report at a lower significance value because they have meaning to the study, because of knowledge from prior studies or whatever. And people, immediately might say, well, that's arbitrary, how do we know? But again, there is a lot of arbitrariness involved. And as researchers, you should be able to make the case for your extra regions of interest and leave that up to the scientific community to decide that in the review process or in questions and discussions. But this allows for more informed discussions. And it's hard for me not to think that showing more information in a reasonably digestible way is going to be better. Standing by choosing p of 0.001, that just seems so arbitrary. It's a little frustrating that tries to shut down conversation. Okay, now let's expand this idea a little bit, taking from these first examples of transparent thresholding maybe being better than opaque thresholding, and staying away from peak voxel statistics because those are so unstable, as we've seen. What are we doing when we report results? Well, we want to try to avoid the problem of wasting information. MRI is a really, really expensive science, and particularly if you're studying subjects that have conditions that make them difficult to scan or is very uncomfortable, that time is just really precious, let alone all the money, grant, training, and these kinds of things that go into it. So it seems like we're behooved as researchers to try to use as much of that information as is possible, while also keeping it reasonable for the community to have in conversation in that. So that's what the point of this paper is, where a lot of these topics are discussed. Okay, let's think about neuroimaging from the point of view of extracting information. You start off with 100 subjects and EPI runs and things like that. You have your raw data, and no one can publish that in a paper. Why? Because there's just too much information. So it's great to have public repositories where people can upload the raw data and other people can get at it and use it. That's great and that's separate. What we're talking about here is reporting results. And there's just simply too much in the beginning, too much information. Well, there's a lot of information, which is good, but it's not very digestible. There's no way you can make a figure out of it or something like that in a paper. So you start off with a lot of information. What do? You process it, and some of that involves reducing the information content. You reduce down your 100 subjects to group level maps, for example, things like that. So as you take your information and churn it, you are reducing hopefully some noise and things like that, but there's less information there. You might just get it down to an effect estimate and statistical map. And some people choose then to only show the statistical map, which loses important information. Some people then, and in many cases, you threshold the statistical map, and now you dichotomize it to only show significant clusters. And then maybe you show only peak statistics out of that. In each of these steps, you are losing information. Why do people keep doing that? Well, because it keeps getting more and more digestible. People often talk about the story of scientific reporting. The story becomes kind of easier and easier. With peak statistics, you just have 10 or 12 or something locations to talk about, and that's easy to discuss. So there is a trade-off here and a balance. We definitely have to increase the digestibility of data from its raw state to something we can publish, but we have a choice about how far along here to go. And we have to remember that we have to balance the fact that as we get more digestible, we are losing information. Okay, so this is something that we talked about already in an earlier part of this video, the difference between using both the effect estimate and the standard error, or only the statistic here. But let's take a look at this in pictures. So by the time you've done your processing and you get to group level results, consider this group level results an unthresholded statistic map. Well, what does it mean to do something like translucent or transparent thresholding that we talked about? You reduce this into something that's definitely more digestible, but we've lost a little bit of information. We don't know exactly what the statistic was in this part of white matter or this part of gray matter than we do here, but we're saying that information loss for digestibility is maybe a reasonable trade-off. What could we do further? We could decide to, you know what? I want an even simpler story. Let's just threshold opaquely so I don't have to discuss or think about anything here. And what could we do further? We could reduce those clusters down to just peak voxal locations. And if you notice, there is one peak here, if you can see it on your screen. The other peaks are in different slices. So we've really reduced the information content a lot, but it's very easy to just talk about now a few peak locations. And this is how you should think about moving down this chain of digestibility and information content in the results. Okay, hopefully that makes sense. And so if we think about how these things are lined up, I would probably make the case that now as we think about which of these we might want to choose, having unthresholded data, in reality, it is more informative, but it just seems a little bit too much. It's hard to interpret visualization problems, to see the underlay and things like that as well. So I would make the case that probably this is a little bit much for an individual paper to report, although again nowadays there are repositories for reporting and uploading unthresholded statistic results and hopefully effect estimates along with it. These here hide a lot of information. Over 95%, or probably even much more than that, information in the brain is totally hidden away in each of these cases. So I think that these suffer from too much information loss. So this one isn't digestible enough. These have a lot of information loss. That leaves our Goldilocks choice, in my view, of the transparent thresholding. It balances digestibility well with kind of minimal information loss, I think, in practice. Okay, so now let's talk about applying these to cross-study results comparisons. All right, we're going to continue using the NARPS data, and now we're going to look at applying this this mindset of trying to show more and see what that actually does for scientific comparisons. So what we're looking at here is the same slice of statistical information for one of the hypotheses in the NARPS team's results, and this is essentially of the 70 teams that submitted results, some of them had results that weren't usable or weren't unthresholded and things like that. So these are the set of all the teams' results that were kind of interpretable. Same slice. And what do you notice here? So this is for one particular hypothesis with all or nothing thresholding applied at a t or z statistic of 3. And different teams reported their results at t or z of using either t or z. For the number of degrees of freedom, because there are 54 subjects here, these are effectively the same thing. So we won't worry about the negligible difference between t and z statistics at the moment. Okay, let's look at these results. Well, so each of these were reported by a different team. And if you look across the first row here, these look pretty largely similar. I see this blue blob here. It has a different size in each case. Okay. I see some red back here and some hints of red here. These kind of largely agree, though the details might be different. And same here. And as I go along, well, what about this group here? If I look at this result seems totally different. This seems maybe what we call high variability or non-reproducible. And as I keep going down, I see more that really look very, very different. Empty, empty, empty here. And now, if I look at this, I might say, well, maybe a third of the results really agree with themselves, but then a lot of them start looking very different. There's a lot of variability here. We have a reproducibility crisis. That might be one way that I would interpret these results. Okay, but let's take a look at these results, applying one of our lessons that using transparent thresholding is more informative. Okay, so this is the same set of results with transparent thresholding applied. What is your visual impression of this now? Well, look here. You see the same hot, cold, hot pattern here, and basically everywhere in this row, and also here, and also here. And look at this data set. This has hot, cold, hot in the exact same pattern as its neighbors. And down here and here, and almost all of these have the same pattern. Let me go back and forth. Opaque thresholding, transparent. Opaque, transparent. Almost the bulk of the data sets now actually have the same pattern of results. They're showing a negative effect here, a positive effect here, positive, negative, that in the same pattern. What is different? There is a difference between this and this that we see, or between this subject and this, or this group and this group's results. It's the relative magnitude of the effect. That is a very different form of variability than saying this is irreproducible and that's irreproducible, or these results don't agree with each other, or these results don't agree with each other. They actually agree to a large amount, just with a different magnitude. And I think this is maybe the central point to this here, that with opaque thresholding, where you're matching blobs, you'll see that there's a lot of overlap in the first row, but then you're going to start perceiving a lot of disagreement, and you're going to interpret that as large variability and lack of reproducibility. Oops. Okay? That is the message when you look at the data this way. When you look at the data with opaque thresholding, you are actually allowed to see much more information, and you see general agreement, but you understand that it's varied strength of agreement, and that is a different form of variation. And this is actually one that, for those who participated in the NARPS study, which our group did, there's actually a lot of flexibility left to researchers. Teams that participated could choose their smoothing radius. And if you look at the results of the NARP study, actually teams picked very different smoothing values. And the difference in smoothness of results was the largest difference that the authors of the NARP study observed. That's a pretty small difference in processing choice to have very different results. And it is entirely possible that that contributes to some of the difference in magnitude. Researchers could also choose whether to use the magnitude of the gambling values that were assigned to weight their results or not, or to orthogonalize rather than using amplitude modulation. And whatever threshold could be used, what kind of quality control to do, whether to exclude subjects or not, all of these things which are realistic to the amount of variable choices in the field, but there was actually a fair amount of variability left up to the researchers. And so this amount of varied agreement of strength of results seems reasonable to me. So there really is a choice. So what is the outcome of this? The simple choice of whether to use opaque thresholding or transparent thresholding totally affects your meta-analysis or your view of the comparison of the results here. Now, it is true there are some down here that have actually an opposite pattern of cold, hot, or cold, hot. What's happening here, actually, when we look at the results here, we can see that these people made probably either a sign mistake or a different choice of interpretation of how to assign the sign of their response. And in some of the hypotheses, it was actually fairly confusing because you're talking about reporting on the result, the negative effect of loss, or the positive effect of loss, or the negative effect of gain. And it is true that different teams could choose different signs. And actually in the NARP's paper, the authors discussed the fact that they did have some feedback and choices with teams that had what appeared to be exactly opposite results. And in many cases, those discussions clarified and improved the matching of these results to the other studies. So having more informed discussions and also thinking about results as contributing to a body of literature that are part of a discussion actually helps, well, in this case, help reproducibility, but in any case helps comparisons. So again, this choice of opaque thresholding, which the field currently tends to adopt, actually tilts you toward thinking that there's high variability and irreproducibility when the reality of the situation is using more informed results reporting is simply that is not the case, that it's variability of strength. We can quantify this in a different way using similarity matrices. So this is if you use dice coefficients of overlap of either your positive or negative clusters, you do see that there's some overlap of positive clusters or certainly of the negative clusters, but it's of a relatively small fraction of the group, certainly for positive clusters, and maybe not the highest values. When you compare the results in a way that's consistent with the highlighting method, the transparent thresholding, so you look at a correlation of the brain maps, a spatial correlation, what you see is there is a huge chunk of data that actually agrees in terms of correlation. Those hot-cold patterns are consistent across a huge fraction of the group. And what do we see? There's also this other highly correlated amongst themselves, but anti-correlated to the bulk of the group, other subjects. This is simply that set of subjects that probably has a sign difference or sign mistake. So this bulk of subjects is nothing more than most of the rows here of subjects, and then that small square at the bottom was these few subjects here that are kind of anti-correlated to these, and those would probably be sorted out. And it is true, there are a few subjects, maybe 3 or 4 teams' results, that are just different to everything. And I think that's pretty reasonable to expect in a study. For example, this group only has positive results, so they're just reporting something different, and maybe there were different modeling or processing choices in some of these as well. I'm not surprised by that. And is having a huge amount of agreement, but with a slightly different magnitude of response effect estimate different? Is that unexpected? Is that a variability crisis? I don't think so. And also, remember, some people will say, well, the NARP study wasn't about the whole brain, it was about specific hypotheses. If we look at the same thing for specific hypotheses, well, The dice coefficient of the positive coefficient for this particular hypothesis 3 is quite low, and certainly for the negative dice. But look at this. If you use the more informative comparison, you have a huge amount of agreement, even more than if you look at whole brain results, actually, especially once you account for the sign difference in these people. So this idea that using more information gives you a more detailed comparison, in this case, that more detailed comparison is not pointing you at non-reproducibility. It's actually pointing you at much higher reproducibility if you use more information. And I'll note that this comparison was something that Rick Reynolds and the group had suggested doing when we were discussing these results and this difference early on. And I noticed that actually later when I was reading the NARP's paper itself, something that I had missed, so this is the paper, their figure 2 actually reports essentially this thing. So they actually showed in their main paper, and I think what was lost certainly on me as a first time reading it, and by many people who discussed it, particularly on the all-knowing Twitter, that high variability, surprising and fMRI methods lead to high variability and things like that. I don't think that is the message that should have been taken away from this paper. So I know the title refers to variability, and some of the abstract reports that as its primary finding. This paper actually does discuss the idea of the correlation, the spatial correlation shows higher similarity. I think basically I find it unfortunate that that was not the primary message, because for me that is the primary message. I would like to think about results in the more full way like this, and this finding actually was their figure 2. This probably should have been the more primary message that this really matters. So I kind of view the NARP's study results as not so much saying that there's variability due to processing methods, but that if you insert opaque thresholding before your meta-analysis, so if you compare this versus this, you are actually setting yourself up for high variability, reproducibility, crisis type issues. If you use more informed comparisons, you're going to get a better meta-analysis and a more realistic picture of the situation. It won't always lead you to seeing high reproducibility. I do think in this study, actually, there is very high reproducibility here, especially once you have the conversation about the signs with these participants. So this is actually kind of a plea to the field to improve its results reporting. And if you report your results like this in a figure versus like this, you really are missing out on very important information, both for your own interpretation and for others, and it harms the way we look at data in the field. So now another thing to note is that that this kind of thing applies to other hypotheses as well. So the same thing applies with other hypotheses in NARPs. So again, if you use transparent thresholding, you see a high degree of similarity across most of the groups. And this is what the similarity matrices look like in this case. So this is for the hypotheses 2 and 4. The first example we looked at were 1 and 3. This is for hypothesis 6. And again, you will see some difference here. I'm not arguing that, but it's that the difference is in magnitude. There are lots of other things to take away from the NARP's results. Several of the groups actually agree in their individual yes-no region-wise hypothesis. They often just agree that there is no effect in some area. And you can actually see some of that from the way we report results here. That you see information, but there actually is a lot of weak effects in some of these specific hypotheses. That is okay for the teams to agree on in large part, that there are weak effects somewhere. They actually still even agree on the sign of those effects, which you can see in this way of reporting. It is not irreproducible just to say that everyone agrees there doesn't seem to be an effect there. So, okay. Conclusions then. This idea of reporting more results and being more informative about them so that the meta-analyses, comparisons, or even simply your own visual interpretation of the results carries more information, what we call the highlighting methodology, under a large umbrella of that term, is really important. It doesn't just aid reproducibility. More importantly, it improves understanding of the data, and it improves the accuracy of your comparisons. I suspect that just like in the NARPS results, it will greatly improve reproducibility in many cases. Thinking of what is a study is something that provides evidence about a given effect or an observation or some kind of results more generally. It doesn't provide the answer. It doesn't have to decide this is significant, that's not. As we've shown, there's biological, mathematical, and statistical problems with that. A study should be considered part of a conversation, not the answer that has decided where things are significant and not. Showing more data in a highlighting way really balances providing more information and more information in a digestible way. And there's lots of ways that you can do this highlighting methodology. We talked about why peak voxel reporting is really, really, really unstable and is going to set yourself up for irreproducibility. They're also in the highlight paper that I showed earlier by Gang Chen et al., that there are other things that apply to this with ROI-based studies, and we've reported on this as well. So this all or nothing thresholding and kind of saying, well, I need to only report things or only look at things at P of 0.001 and 5% family-wise error, everything else is wrong and non-scientific, that frankly sounds good until you're looking at it a bit more and think about the problems that really come along with it, such as the sensitivity to arbitrary values, hiding of artifacts, biasing yourself toward irreproducibility, and other things like that. So again, I understand why the argument comes up for that, but looking at it more deeply, there's really a lot of problems that come with it. Cross-study comparisons, as we've shown here, and even kind of with the NARPS data itself and what was a secondary analysis there, I think should have been the primary message, using unthresholded results or weighted results by the statistical evidence really, really matters for improving your meta-analyses. If you just threshold your data, you're going to be strongly biased. So hopefully this is something that the field will adopt in maybe kind of a grassroots way. This is a choice that every researcher has to make about their own data. This paper has been out for a while. It didn't make the same splash that the NARPS study made about variability, or that previous studies have been made about emphasizing the p-value and things like that. And I'm not sure why. But anyways, I feel that this is something that's maybe more important than some of the other things that have been emphasized in results reporting before for reproducibility and things like that. And it's also worth noting that you can upload unthresholded results and things like that. But remember, for me to make the argument here, or for our group and others who worked on this project to make the argument here that the highlighting, thresholding really matters, that this is not the full story, but this is, I had to go download the data and spend a year plus of work analyzing it, reanalyzing it, writing the paper. And this secondary message is probably not as prominent as the initial one about variability. If the results had been reported like this, or if an image like this had been shown, this would have totally affected the interpretation within the paper and also people's results to it. But in essence, this is the message that was shown. And so simply the way you present your results really affects your own interpretation and how other people will view it. So anyways, I'd like to make the case that something as simple as, a figure is worth 1,000 words, or a picture is worth 1,000 words, it's probably worth even more than that, even in this day and age of data sharing and things like that. So hopefully the field will move to adopt this and maybe improve comparisons and things like that. These are some of the papers that were cited here.